Dear students, welcome to the lecture on strain energy of deformation. This lecture covers the second part of Module 4 of the course Advanced Mechanics of Solids. This lecture will cover the topics: what is strain energy of deformation, then we will derive the general expression for strain energy, and also we will derive the expression for strain energy in 4 specific cases, namely case 1, bar subjected to an axial force; case 2, a block subjected to a shear force; case 3, a beam subjected to a bending moment; and case 4, a shaft subjected to a torque. Also we will see what is influence coefficient, and finally we will learn reciprocal relation, and also we'll see the proof for the same. Problems in elasticity can be solved by 2 different methods. The first one is Newtonian mechanics, where we make use of the equations of equilibrium. And the second method is Lagrangian mechanics, where we make use of the principle of conservation of energy. The reason why we study about strain energy of deformation is because energy methods provide a powerful tool for deriving exact and approximate solutions to many problems in elasticity. Energy is a scalar quantity, so energy methods are also called scalar methods. Energy methods are based on linear elastic behavior and conservation of energy. That is, the work done by the external force is equal to the energy stored in the structure under the load. Energy methods are extremely useful in solving indeterminate problems, problems involving impact loads, and instability problems in elasticity. Now, we will see what is strain energy. When a body undergoes deformation under the action of externally applied forces, the work done by these forces is stored as strain energy inside the body, which can be recovered when the body is elastic in nature. Thus, strain energy of a member is defined as the increase in energy associated with the deformation of a member. Strain energy is usually denoted by capital letter U. The strain energy stored in an elastic body can be found out by equating the external work done by the applied loads to the internal energy stored in the body. Also, the strain energy density of a material is defined as the strain energy stored per unit volume. Now, we will derive an expression for the strain energy in the case of an infinitesimally small stress element which is subjected to an uniaxial state of stress along the x direction. Consider an infinitesimally small element of size dx, dy, and dz. The force acting on the two faces, whose normal is along the x direction, is given by sigma x into dy into dz. Let epsilon x be the strain along the x direction. Then we have elongation of the element due to the force along the x direction equal to epsilon x into dx. The force increases from 0 to sigma x into dy into dz during the elongation. So, the average force during the elongation is given by sigma x into dy into dz by 2. We know that the work done is given by average force into distance. The work done on the element is stored as strain energy. Thus, the expression for the strain energy du is equal to average force into distance. That is, du is equal to half into sigma x into dy into dz into epsilon x into dx equal to half sigma x epsilon x dv. Now, if we consider this stress element as a part of a structure which is subjected to an uniaxial force, we can get the expression for the strain energy stored in the entire structure as U is equal to half into integral over the volume V sigma x epsilon x dV, where V is the volume of the structure. In elasticity, the most general state of stress is this three-dimensional state of stress as shown in the figure, where we have all the 6 components of stress. Now, in the case of a body which has all the 6 stress components present, the general expression for the strain energy is given by U is equal to half into integral over the volume V sigma x into epsilon x plus sigma y into epsilon y plus sigma z into epsilon z plus tau xy into gamma xy plus tau xz into gamma xz plus tau yz into gamma yz into dV, where V is the volume of the structure. So this is the most general expression for strain energy. Now, coming back to the stress element which is subjected to uniaxial state of stress, if we plot the force versus displacement by taking the force sigma x into dy into dz along the y direction and the displacement epsilon x into dx along the x direction, for a linearly elastic element, we will get the curve as a straight line, as OA represented in the figure. The area under the curve OA is given by half into sigma x epsilon x into dx into dy into dz, which is the same as the strain energy stored in the element. Thus, we say that for any structure, the area under the force displacement curve will give the strain energy stored in the structure. Now, if we make a similar plot of stress versus strain during the loading of the linearly elastic stress element, we will get a curve OB as shown in the stress strain curve. The area under the curve OB is given by half into sigma x into epsilon x, which is the strain energy stored per unit volume or the strain energy density. The slope of the stress strain curve gives the modulus of elasticity E for the material. I will introduce you to the concept of complementary energy. The force deflection space is divided by the force displacement curve into 2 regions. One is the area beneath the curve OA, and the second is the area above the curve OA. As we have already seen, the area of the region under the curve is the strain energy stored in the structure. The area in the force displacement space above the curve gives the complementary energy. Complementary energy is usually denoted by capital letter C. In the case of a linearly elastic body, the complementary energy is equal to the strain energy stored, that is C is equal to U. Complementary energy has the same unit as that of strain energy, but complementary energy has no physical meaning. Even though complementary energy has got no physical meaning, the concept of complementary energy is used for solving problems in using energy methods. Strain curve for two different materials, namely material 1 and material 2, is shown in the figure. As we can see, the stress value at the point of rupture for material 1 is much greater than that of material 2. So that means material 1 is stronger than material 2. Now, we have already seen that the area under the stress strain curve gives the strain energy density or the strain energy stored per unit volume. So as we can see from the figure, the strain energy stored per unit volume for material 2 is greater than that of material 1. This means material 2 is tougher than material 1. So what is toughness? Toughness is the ability of a material to withstand impact load. So this means that material 2 can withstand more impact load as compared to material 1. Now, if we take a closer look at the stress strain curve of material 2, the portion OA of the curve is a straight line. That is, if we load the material up to point A, as we remove the load, the structure will regain its original shape. The area under the curve OA is called the modulus of resilience. And modulus of resilience represents the energy per unit volume that the material can absorb without yielding. Now, we will derive the expression for strain energy in 4 different cases. First, in the case of a bar which is subjected to an axial force. Second, in the case of an element which is subjected to a shear force. Third, in the case of a beam which is subjected to a bending moment. And fourth, in the case of a shaft which is subjected to a torque. We will begin with the derivation for strain energy in the case of a bar which is subjected to an axial force. Consider a bar of length L and an uniform cross-section A. The bar is subjected to an axial force F. Let X be the extension of the bar due to the force F as shown in the figure. The force displacement curve for the bar is shown in the figure. Work done by the force is equal to the average force into the displacement, that is half F into X. The work done is stored as strain energy. So strain energy U is equal to half F into X. We know that the stress developed in the bar sigma equal to force F divided by the cross-sectional area A, and the strain epsilon is equal to the increase in length X divided by the original length L. Substituting for force, that is F equal to sigma into A, and for the increase in length X equal to epsilon into L, in the expression for strain energy, we get strain energy U equal to half sigma into A into epsilon into L. We know that the cross-sectional area A into L will give the volume of the bar. So the strain energy U is equal to half sigma into epsilon into volume. Now, if the axial force in the bar is not uniform along the length of the bar, or if the cross-sectional area is not uniform along the length of the bar, we can write the general expression for the strain energy stored in the bar, which is subjected to an axial force, as U is equal to integral over the volume V half sigma epsilon into dV. By Hooke's law, the Young's modulus E is equal to stress by strain, that is sigma by epsilon, or epsilon is equal to sigma by E. Thus, we get the expression for the strain energy as U is equal to integral over the volume V sigma square by 2E into dV. In case 2, we will derive the expression for strain energy in the case of a block which is subjected to a shear force. Consider a block which is subjected to a shear force in opposite directions as shown in the figure. Let A be the area of the top and bottom face of the block, and H be the height of the block. The top face of the block slides with respect to the bottom face by a distance x as a result of the shear force. The force displacement curve is shown in the graph. As we have already seen, the strain energy stored U is equal to the work done by the external force F, that is U is equal to half F into X. The shear stress tau is given by shear force F divided by the shearing area A, which gives force F is equal to shear stress tau into the area A, and shear strain gamma equal to X divided by H, which gives X is equal to gamma into H. Substituting in the expression for strain energy will give strain energy U is equal to half tau into gamma into A into H. A into H will give the volume of the block. So strain energy U is equal to half into tau into gamma into volume. This general expression for strain energy in the case of a shear stress is given by strain energy U is equal to integral over the volume V half tau gamma dV. The modulus of rigidity G equal to shear stress tau divided by gamma, that is shear strain gamma is equal to tau divided by G. So we get strain energy U is equal to integral over the volume V tau square divided by 2G into dV. In case 3, we will derive the expression for strain energy for a beam. Consider a beam of length L and supported at its ends and is subjected to a distributed load and a point load as shown in the figure. Consider an elemental length dx of the beam at a distance x from the left support. Let M be the bending moment acting on the element as a result of the load. In the third semester, we have already studied that beam bending formula or the flexure formula, which is given by M by I is equal to sigma by Y, or sigma equal to M into Y divided by I, where sigma is the normal stress on a fiber which is at a distance Y from the neutral layer. M is the bending moment and I is the moment of inertia of cross section with respect to the neutral axis. In the case of a beam, the only significant stress is the normal stress. We have already derived the expression for strain energy in the case of an element with uniaxial state of stress. We use the same formula in the case of the beam, and we get strain energy stored in the beam U is equal to integral over the volume V sigma square by 2E into dV. Substituting for sigma, that is sigma is equal to my divided by I, we get strain energy U equal to integral over the volume V 1 by 2E my by I the whole square into dV. The above volume integral can be written as integral 0 to L 1 by 2E m by I the whole square into integral over the area A y square dA into dx, because only y varies across a cross section and m is a constant for a particular cross section. This can be again rewritten because integral over the area A y square dA is equal to I, this moment of inertia of the cross section with respect to the neutral axis. Substituting, we get strain energy U is equal to integral 0 to L 1 by 2E m by I the whole square into I into dx. That is, strain energy stored in the beam U is equal to integral 0 to L m square divided by 2EI into dx, where m is the bending moment in the beam in terms of x, E is the Young's modulus, and I is the moment of inertia of cross section about the neutral axis. And in case 4, we will derive an expression for the strain energy in the case of a shaft which is subjected to a torque T. Consider a shaft of length L and radius capital R, which is fixed at one end and is subjected to a torque T at the free end as shown in the figure. Let AB be a generator of the shaft. The free end of the shaft twists with respect to the fixed end by an angle theta as a result of the applied torque T. After the twist, the point B will take a new position B dash. Gamma is the shear strain. The strain energy stored U is equal to work done by the external force. That is, U is equal to half T into theta. We have already studied the torsion formula for a shaft subjected to a torque T in the third semester. That is, T by J equal to tau by R equal to G theta by L, where J is a polar moment of inertia which is equal to pi r raised to 4 by 4. Tau is the shear stress in the shaft at a radius small r. G is the modulus of rigidity of the shaft. The shear stress tau will be maximum at the outer radius, that is, where small r is equal to capital R. This gives T by J equal to tau max by R equal to G theta by L, which gives theta is equal to T into L by J and T equal to J into tau max by R. Substituting for theta and T in the expression for strain energy, we get U is equal to half into J into tau max by R into L by J into J into tau max by R. That is, the expression for strain energy for a shaft subjected to a torque is given by U is equal to tau max square divided by 4G into volume. The general expression for the strain energy stored in the shaft is U is equal to integral over the volume V in tau max square by 4G into dV. To summarize the expressions for strain energy we have derived for the various cases. In the case of a bar subjected to an axial force, strain energy U is equal to integral over the volume V sigma square by 2E into dV. In the case of a block which is subjected to a shear force, the strain energy U is given by U equal to integral over the volume V tau square by 2G into dV. In the case of a beam, strain energy U is equal to integral 0 to L m square by 2 EI into dx. And in the case of a shaft which is subjected to a torque, strain energy U is equal to integral over the volume V tau max square by 4G into dV. The general expression for strain energy is given by U is equal to half integral over the volume V sigma x epsilon x plus sigma y into epsilon y plus sigma z into epsilon z plus tau xy into gamma xy plus tau xz into gamma xz plus tau yz into gamma yz into dV. Now we will study what is influence coefficient. When we studied the generalized Hooke's law in module 2 of this course, we have seen that the 6 rectangular stress components are related to the 6 rectangular strain components at the same point through a set of linear equations. Hooke's law is applied to elastic body as a whole. It asserts that deflection in a body are proportional to the forces which produce them, irrespective of the shape or size of the body. The figure shows a body of arbitrary shape supported at 3 distinct points. Force F1 is applied at point 1 on the body, which is in equilibrium. As a result, point 2 on the body undergoes a deflection which, according to Hooke's law, is proportional to F1. The deflection at point 2 may take place in a direction which is quite different from that of F1. Let capital D2 be the actual deflection at point 2. Then we have capital D2 equal to K21 into F1, where K21 is a proportionality constant. Let small letter d2 be the component of capital D2 in a specified direction. Here in this particular case, the specified direction is vertical. Theta be the angle between capital D2 and the vertical. When we are interested about the deflection in a specified direction, in this particular case it is vertical, the theta value will be a constant. So K21 into cos theta will be a constant, and the above equation becomes small letter d2 equal to capital D2 into cos theta equal to K21 into cos theta into F1. That is small d2 equal to A21 into F1, where A21 is a constant and is called influence coefficient for vertical deflection at point 2 due to a force F1. The displacement at point 2 in a specified direction due to a force F1 applied at point 1 is proportional to F1. In the equation D2 equal to A21 into F1, when force F1 is 1 unit, we will get D2 equal to A21. This gives the definition for the influence coefficient A21. Influence coefficient A21 is defined as the displacement produced at point 2 in a specified direction due to a unit force applied at point 1. Now consider the example where instead of a single force F1, several forces F1, F2, F3, etc. up to Fn are acting simultaneously on the body. The vertical deflection at point 2 due to the force F1 is given by A21 into F1. The vertical deflection at point 2 due to the force F2 is given by A22 into F2. The vertical deflection at point 2 due to the force F3 is given by A23 into F3. Likewise, the vertical deflection at point 2 due to the force Fn is given by A2n into Fn. When the forces F1, F2, F3, etc. up to Fn are acting simultaneously on the body, the resultant deflection at point 2 can be found out using the principle of superposition. That is, in an elastic body, if several forces F1, F2, F3, etc. up to Fn are applied simultaneously, the resultant vertical deflection produced at 2 will be the resultant of deflection which these forces would have produced if applied separately. This is called the principle of superposition. Thus, the resultant vertical deflection at point 2 is given by d2 equal to a21 into f1 plus a22 into f2 plus a23 into f3 plus etc. up to a2n into fn. In the figure, we see a body which is supported at 3 points, namely A, B and C. Forces F1 and F2 acts at points 1 and 2 respectively. Let capital D1 represents the resultant displacement at point 1. The component of capital D1 along the direction of force F1 be delta 1. Delta 1 is called the corresponding displacement at point 1. Similarly, at point 2, the component of the resultant displacement along the direction of application of force F2 is called the corresponding displacement at point 2, and it is denoted by delta 2. Thus, the corresponding displacement at any point where a force is acting is the component of the resultant displacement at that point along the direction of the application of the force. Corresponding displacement is also called work absorbing component of displacement because at any point the product of the force acting at that particular point and the corresponding displacement will give the work done by the force at that particular point. It may be noted that when we are considering the force for the calculation of the work done, the average force should be taken. Now, in the figure, the points of support A, B and C do not yield, and hence the corresponding displacements at these points are 0. In general, for a body which is subjected to forces F1, F2, F3, etc. up to Fn, as per the definition of influence coefficient and applying the superposition theorem, the corresponding displacements can be expressed as delta 1 equal to A11 F1 plus A12 F2 plus A13 F3 etc. plus A1n Fn, and delta 2 equal to A21 F1 plus A22 F2 plus A23 F3 plus etc. up to A2n Fn. Likewise, the corresponding displacement at point n is given by delta n equal to an1 f1 plus an2 f2 plus an3 f3 plus etc. ann fn. Consider a body which is supported at 2 points, acted upon by forces F1, F2 and F3. The corresponding displacements at points 1, 2 and 3 be delta 1, delta 2 and delta 3 respectively. During the displacement delta 1 at point 1, the force increases from 0 to F1. So, the work done by the force F1 is W1 is equal to half F1 into delta 1. Similarly, the work done by force F2 is W2 equal to half F2 into delta 2. And the work done by the force F3 is W3 equal to half F3 delta 3. Total work done, W is equal to W1 plus W2 plus W3. In general, in an elastic body which is acted upon by n forces F1, F2, F3, etc. up to Fn at n different points, if the corresponding displacements be delta 1, delta 2, delta 3, etc. up to delta n, the strain energy stored in the body is given by U equal to half into F1 delta 1 plus F2 delta 2 plus F3 delta 3 plus etc. up to Fn delta n. Now we will study an important relationship regarding the influence coefficient, that is the reciprocal relation. Reciprocal relation states that the influence coefficient Aij equal to Aji. The proof: consider a linearly elastic body acted upon by a force F1 at point 1. The energy stored is given by U1 is equal to half F1 delta 1, which is equal to half A11 F1 square, because delta 1 equal to A11 into F1. Now on this body we apply a force F2 at point 2. The deflection at point 1 will be A12 into F2, and during this displacement at point 1, complete force F1 is already acting. So the work done by the force F1 is F1 into A12 F2. The deflection at point 2 is given by A22 into F2. The energy stored when F2 is applied is given by U2 is equal to half into F2 into A22 F2 plus F1 into A12 F2. The total strain energy stored in the body is given by U is equal to U1 plus U2, that is equal to half into A11 F1 square plus half A22 F2 square plus A12 into F1 into F2. Consider the same linearly elastic body, but now the force F2 is applied first and then F1. Strain energy stored in this case is given by U dash equal to U1 dash plus U2 dash, where U1 dash equal to half A22 F2 square and U2 dash is equal to half A11 into F1 square plus A21 into F1 into F2. Since the strain energy is independent of the order of application of F1 and F2, we have U equal to U dash. So half A11 F1 square plus half A22 F2 square plus A12 F1 F2 equal to half A22 F2 square plus half A11 F1 square plus A21 F1 into F2. Hence we get A12 equal to A21, or in general Aij is equal to Aji. Thus the reciprocal relation is proved. We had already derived the expression for strain energy stored in an elastic body which is subjected to n number of forces F1, F2, F3, etc. up to Fn. Now here we will substitute the expressions for the corresponding displacements delta 1, delta 2, etc. up to delta n. That is, the corresponding displacement delta 1 is equal to A11 F1 plus A12 F2 plus A13 F3 plus etc. up to A1n Fn. Likewise, the corresponding displacement delta n is equal to an1 F1 plus an2 F2 plus an3 F3 plus etc. up to ann Fn. Also, we will use the reciprocal relation Aij is equal to Aji. That is, A12 equal to A21, A13 equal to A31, and so on. So we will obtain the expression for strain energy stored as U is equal to half of A11 F11 square plus A22 F22 square plus A33 F33 square plus etc. up to ANN FNN square plus A12 F1 F2 plus A13 F1 F3 plus etc. up to A1N F1 Fn plus A23 F2 F3 plus A24 F2 F4 plus etc. up to A2N F2N Fn plus this will continue, and the last term will be ANN minus 1 Fn Fn minus 1. This expression for strain energy stored is very important, and we will be using this expression in the subsequent presentation on strain energy methods. Before I conclude, let me just summarize what we have learned in this lecture. We began our discussion with what is strain energy of deformation. Then we derived a general expression for strain energy stored in an elastic body. Also, we have seen what is complementary energy, and we learned what is toughness, strength, and modulus of resilience. Next, we derived the expression for strain energy in 4 specific cases which we come across quite frequently in elastic problems. And finally, we learned about the influence coefficient, reciprocal relation, and also we derived an expression for strain energy stored in an elastic body in terms of influence coefficient. With this, let me conclude. Thank you very much, students, for your patient listening.